Hi, welcome everyone. It's a pleasure to introduce today's seminar speaker. It's Erica McGrath-Spangler from the Global Modeling and Assimilation Office at Goddard Space Flight Center. And so by way of introduction, Erica did her bachelor studies at the University of Wisconsin in Madison, where she did a double major in atmospheric and ocean sciences and mathematics. And her cumulative GPA was more than 3.9. And then she for her graduate studies, she went to Colorado State University, where all graduate students in that department do first a master's degree and then they go on to a PhD degree. And so both of her theses for the master's and for PhD were about entrainment effects in the boundary layer on land-atmosphere interactions and fluxes of tracers like carbon dioxide or water vapor. And then since June of last year, she is a postdoctoral research scientist at Goddard Space Flight Center. So let us welcome Erica McGrath-Spangler.
Hello? Okay, I think it's working. So thank you again for everybody having me. Thank you to Sultan for that very nice introduction. Got an opportunity to meet a couple of you this morning, so I've really been enjoying my visit. Please interrupt me if you have any questions during the presentation. I don't think I've ever given a seminar talk without being interrupted at least once. So please don't feel shy. I'd love it if you ask the questions, so that way you don't forget at the end. So as my title shows, I'm going to be talking about global seasonal variations of planetary boundary layer depth. This is part of my PhD work that I did with Scott Denning at Colorado State University, and part of my my postdoc work that I'm working on with Andrea Millad at NASA Goddard. Okay, so first, just a quick outline. I'm going to go over some introduction and motivation. Sort of why do we care about the boundary layer? You know, why is it important? Look at boundary layer depth derived from the Calypso satellite. Then look at boundary layer depth from the GEOS 5 model. That's the model that's used within the GMAO, the group that I'm working with at Goddard. And then finish with some conclusions. Yep. Okay. So introduction and motivation. So what is the planetary boundary layer? Or it's also called the PBL. It's the turbulent layer closest to the Earth's surface. It determines the surface fluxes of heat, moisture, momentum, trace gases. It interacts with clouds, radiation, convection, aerosols, pollutants. It's especially important for the transport of water vapor. Water vapor is evapotranspiration near the surface. It goes through that boundary layer. It's affected by PBL processes, and then it rises to the top to form clouds, precipitation, things like that. It's also important for momentum. Momentum has to travel through the boundary layer to get down to the surface where it's dissipated by friction. And it's really important for scalar quantities like CO2, water vapor, heat, because they're diluted by the depth of the boundary layer. Okay, so what does the boundary layer look like? So the diurnal evolution of the boundary layer, it has sort of a maximum during the midday. And this is after a morning transition where it starts to grow. And then during the evening transition at night, it's undercut by a stable layer. And then above that stable layer is a residual layer where it still sort of maintains those properties of that diurnal, that daytime boundary layer. And it's capped by an entrainment zone, which is where you have mixing between the boundary layer and the free troposphere. And then there's a capping inversion, usually within that entrainment zone and throughout the nocturnal boundary layer. And it's important because tracers emitted at the surface, that's your water vapor, that's your aerosols, it's your CO2, are mixed by turbulence, and their concentrations are going to depend on that boundary layer. Okay, so what do I mean by that? So the concentration of a aerosol or tracer is inversely proportional to the depth of the boundary layer. So a deeper boundary layer will dilute a flux signal relative to a shallower boundary layer. And what it means is that in models, we need to be able to get that depth of the boundary layer right if we want to get that concentration, that surface concentration correct. So if we start with two different boundary layers, one's shallow and one's deep, and we have an equal surface flux in both of those boundary layers, the turbulence is going to mix those tracers, and when they're being mixed, the deeper boundary layer has a much greater volume that those tracers are being mixed through. So that's going to have a lower concentration in that boundary layer. If you look at a shallow boundary layer, that concentration is going to be higher because there's just less air for it to mix through. So another way to look at this, if you have two glasses of water, and I always threaten I'm actually going to bring in water and food coloring, but I don't think the airport would have let me do it. So if you have two boundary layers, one's deep and one's a half glass, and actually I did this on a Mac, and this is on Windows, so it's missing the line. This should have a line about here showing the deep boundary layer, and the half glass should have a similar line showing the shallow PBL. And we add a CO2 flux. This could also be aerosols, it could be pollutants, it could be water vapor, but we add some sort of flux to those glasses, represented by food coloring. And then we mix the food coloring through the volume of water, and on the left, and when you have the deep boundary layer, you're going to have a lighter color from that food coloring. And the shallow layer is going to have a darker color. And that's showing the different concentrations. And so even though we have the exact same flux, the same amount of food coloring into both glasses, the deep boundary layer is going to have a smaller impact than the shallow boundary layer. So this is really important for inverse modeling. My background is actually CO2 carbon budget studies, and why does the boundary layer depend on, or why does CO2 depend on the boundary layer? Why is the boundary layer important for carbon? And so inverse modeling, one of the things we do is we take an observation, we have an air parcel, and we take a sample from it. We measure the CO2 in that air parcel. And then it travels around. It goes over factories and cars, it goes over forests, and so that it's getting sources and sinks of CO2 as it's traveling around. And then we sample it again at the end. And we can say something about the horizontal transport. Where did it evac? Did it go over a city or did it go over a forest? And so that says something about those sources and sinks. But it depends, those concentrations that we're measuring in these two air samples, and the two air samples, that depends not only on the horizontal transport, but it also depends on the vertical transport. Are those concentrations, was the boundary layer really shallow when it went over that factory, or was it really deep? Similarly for the forest. So what if we don't know the vertical transport? If we don't know the vertical transport, we can't really determine what those surface fluxes were. And that's the whole point of inverse modeling, is to try and determine what were those surface fluxes. So you have to be able to make assumptions. And that's sometimes hard because boundary layer processes are often small scale and not resolved by models. My work now is using global models, and so you have a grid box, half a degree if you're lucky, and you're not going to be able to resolve those small eddies that are occurring within the boundary layer. They have parameterizations, they exist, but they're usually based on empirical data from idealized experiments. So people go out over Kansas, they go over Australia, and use the Goddard experiment and try to determine what is the boundary layer doing there. And that's not necessarily applicable to over Washington, D.C., where I live currently, or over New York. They also have different methods that exist to try and determine the boundary layer depth. You can determine the boundary layer depth based on turbulent kinetic energy, how much mixing is there going on and how high does that mixing occur. You can look at heat diffusivity, how high is surface heat, how high is that going up. You can look at temperature profiles. That's sort of more of the traditional. You look at a radiosonde, where do you have that temperature inversion? And some of the recent studies that are looking at with radiosondes are actually looking at the bulk Richardson number, which is a measure of TKE production and consumption. So what happens when we try to model the boundary layer? So a couple of things happen. So these are from two different reanalyses. So these are models that have data assimilation, so temperature, winds, and things like that are being incorporated into the model. So it's supposed to be a little bit more realistic than just a straight up regular model. So these are just for sunny midday conditions in the boreal summer 2006 through 2010, and the reason I picked those conditions are because they match the satellite that I'm going to talk about later. And what you see is that they're qualitatively similar. You know, if you look over the United States in the southwest, you know, deserts of Arizona, the Rocky Mountains, things like that, in both reanalyses, both the MERA and NAR, the boundary layer depth is deepest there. It's shallower over the water, and you can get a sort of a qualitative understanding of the boundary layer depth patterns. But you look at the quantitative results, and those are actually very different. The NAR over the southwestern United States is giving a boundary layer depth of about 3.5 kilometers. Did you have a question? Oh, okay, sorry.
Yeah, so are these the heights from the parameterizations or diagnosed from the thermodynamic profiles?
So these are actually the boundary layer depths that are output by the two different reanalyses. MERA actually looks at the eddy diffusivity, you know, how high are things being transported, and the NAR actually looks at TKE. So they're using two different definitions, and these are the ones that the different reanalyses put out, and these are above ground level, so it's not just because it's the high desert that's why boundary layer depth is higher there. Did that answer your question?
Yeah.
Okay.
Was the topography height removed over the Rocky Mountains? I saw some of the red.
Yes. So these are above ground level, so the topography has been removed. Okay. So the NAR is very much deeper than the MERA. You know, NAR is closer to 3.5 kilometers. MERA is closer to 2 to 3 kilometers. And so even though these are both, you know, very sophisticated atmospheric models, they both have observations that have been incorporated into them, they're still giving different boundary layer depths, which is important if you want to look at, you know, how is water vapor being transported from the surface up through the boundary layer. If you want to look at carbon dioxide, these sorts of things are important. So why are we getting two different measures of boundary layer depth, even though they're both taking into account observations? Well, the PBL is hard to observe. It's during midday, it's about 1 to 2 kilometers above the ground, so you can't just step outside with a thermometer and see, oh, that's what the boundary layer depth is. They have multiple different ways of measuring it. Wind profilers and aircraft have been used quite a bit, but they're pretty expensive, so they're limited temporally and spatially. They're also mostly deployed during field campaigns to try and measure the boundary layer depth in very select situations. Radiosondes are sort of the gold standard. Those are what sort of the go-to is if you want to determine what the boundary layer depth is, because that depends on temperature and winds and things that people generally associate with the boundary layer. But those are usually only launched at 2 times, 0 and 12 UTC. Here in the United States, that's actually during the transition times. That's during the morning and the evening, so you're not going to get that maximum boundary layer depth if you're only looking at the standard radiosondes. And on top of that, radiosondes are point measurements. You know, just where did that balloon go? And so, I'm sorry, so they only measure one point in space and time, and they can differ from the average by up to 40%. So what I did is, this was part of my PhD work, is we said we want to know what the boundary layer depth is, and we don't want to be restricted to looking at only morning and evening. And so we went to satellites. So CALIPSO stands for the Cloud-Aerosol, Lidar, and Infrared Pathfinder Satellite Observations. Kind of a mouthful, that's why we call it CALIPSO. Much easier to say. It was launched in April of 2006 and had its first light in June of that year. So that's when it first started, finished all of its launching operations and started sending back data. And it's part of the 8th train or afternoon constellation of satellites. So if you're familiar with CloudSat, OCO was supposed to be a big satellite that was going to be in the 8th train. They're going to launch OCO2, I believe, sometime next year. So it's quite a few number of satellites that are all observing roughly the same location at roughly the same time. And this is actually a picture of launch. Calypso actually launched along with CloudSat. I just think it's a cool picture. Okay, so this is the satellite track from a single day. So this is sort of like where Calypso is observing. This is just from January of last year. The red is the daytime, and that's actually this part of the satellite track that I look at, is trying to determine that midday boundary layer depth. Blue is nighttime. So it's at 705 kilometers is how high the orbit is, and it has a repeat time of about 16 days. So it's going to repeat this track once every 16 days, and then the other days it's going to move slightly along. So with additional days, you're getting additional coverage. Okay, so Calliope is the name of the Lidar on board Calypso. It is sensitive to aerosols and clouds, and it measures the scatter of a laser beam off of these things, off of the aerosols, off the clouds, off of surface. It has 20 Lidar pulses per second, which translates to about 1/3 of a kilometer horizontal resolution. So every third kilometer, producing an atmospheric profile. The vertical resolution is about 30 meters, so we're getting pretty high vertical resolution as well. It emits light at 1064 nanometers, which is in the infrared, and also polarized light at 532 nanometers, which is green. And the reason I really wanted this laser pointer is that it's the same wavelength as this laser pointer. So if you ever see this color in the sky, that's probably Calypso. So it was the first, sorry, what?
I was just saying, through your binoculars, last thing you'll ever see.
I have been told that if the atmosphere is just right, you can see sort of a faint green glow as it's going by. And there's a website that you can go to that tracks where the satellite's located. So it's the first satellite LiDAR optimized for aerosol and cloud measurements. It requires about 1.7 million laser shots every 24 hours. So that is a lot of data that it's taking in, and it can measure things like dust from the Sahara, those clouds, things like that. And as of June 2011, which is when I went to the Calypso science team meeting, it had 3 billion laser shots, which is just a tremendous amount of data. And for all of that data, the laser had been on for about a minute. So that just shows how much they really try to conserve things when something's going up into space. Okay, so this is just a satellite image from the GOES satellite. And the green line is the satellite track of Calypso, roughly that. And what I want you to know is that there are clouds over the Rocky Mountains. And this is what Calypso sees from that same satellite track. So it's the green part of the satellite track, right here. Altitude in kilometers is along the y-axis. The location is along the x-axis. And it's going over the ocean, the Mexican plateau, and then up into Manitoba. Over the Rocky Mountains. Manitoba's later. The red line is the surface. And so this is sort of what you can see if you're looking at the Calypso data. And you can see clouds, and those clouds are over the Rocky Mountains. So it's actually picking up some of the things that we can see with a big GOES infrared satellite image. We can also see LiDAR shadows. So the LiDAR is actually attenuated as it's going through the clouds. And the signal is being bounced back to space, and it's not making it all the way through the clouds. And so you get sort of a dark spot beneath those clouds. And you can also see those aerosols, that sea salt and dust and all of the things that are being transported within the boundary layer. So this combination of being able to see clouds and aerosols means that we can detect the boundary layer, which is fantastic. Okay, so the method I used was initially developed by Jordan et al. We horizontally averaged it to increase the signal-to-noise ratio. There's kind of a lot of things going on, and so you need to average it to try and bring out some of that signal. And what we do is we identify a local maximum in the attenuated backscatter at 532 nanometers, co-located with a maximum in the standard deviation. This is a vertical standard deviation. And the idea behind this is that entrainment zone sorry, I'm used to the laser pointer being on the thing. That entrainment zone that's on top of that mixed layer, within that layer there's mixing of aerosol-laden boundary layer air, all that stuff in the boundary layer is mixing with the clearer free tropospheric air. And that's creating a lot of variability because you've got aerosol plumes with clear plumes, and it's producing a lot of variability. And so we automated the routine. The Jordan et al. Paper did a lot of this by eye. And with 3 billion laser shots, we were not going to be doing it by eye. So what we did was we searched only between 250 meters and 5 kilometers because the boundary layer shouldn't be too much higher above 5 kilometers. And if it is, then there's something else going on, and that was not necessarily what we were interested in. The 250 meters is because we wanted to avoid surface noise. We didn't want to be accidentally retrieving variability because of a forest or buildings or something like that. And we rejected profiles that are being attenuated by thick clouds. So we've got that big convective cloud cumulonimbus. You can't see through that to get to the boundary layer, and so we rejected those profiles as well. And we identified those clouds using the 1064 nanometer, so that infrared, the same thing as that GOES image, that you can see those clouds over the Rocky Mountains. And so what we did was we just tried to retrieve the easiest. With so much data, we wanted to get sort of the low-hanging fruit first. So this is a sample profile. So this has already been horizontally averaged to increase that signal to noise ratio. You've got height along the y-axis, and then the attenuated backscatter along the x-axis in units of per kilometer per sternian. The black line is the attenuated backscatter. The blue line is the standard deviation. Again, that's vertically computed along four heights. And so the first thing we do is we start searching at the surface. We want to find that surface. We want to make sure that we're not accidentally getting forests and trees and buildings and things like that. So we first find the surface, and we start looking above all that surface noise. And you can see that there's a strong Lidar signal right at the surface, and that's because you've got that laser beam is bouncing off of that and going back up. So we start searching upwards, and we find a maximum in the attenuated backscatter itself, but there's no associated maximum in the standard deviation. So there's not that variability that we expect to find within the entrainment zone. So we keep searching. And so we go up a little bit higher, and then we do find, in this particular profile, at about 1 kilometer, we're finding a maximum in both the attenuated backscatter and in that standard deviation. So we've got a strong signal that also has a lot of variability associated with it. So we say that that is the retrieved boundary layer. And then after we find that retrieved boundary layer, we search above to make sure there aren't a whole bunch of clouds that could have messed with the signal. And in this profile, there aren't. So good, we've got the boundary layer. So then we sort of look at a satellite track. Instead of just looking at a single profile, if we put a bunch of profiles together, what does it look like? So this is already horizontally averaged, so it's increased that signal. We've got height from about 0 to about 5 kilometers along the y-axis, and then the x-axis is the satellite track. It's a subset of the green, oops, I keep forgetting. It's a subset of this green satellite track right here. And so it's going over the Yucatan Peninsula, then over Little Rock, Arkansas, and now we're going up into Manitoba. And the white line is the surface. That's from standard data set of where the surface is located. And we can see a couple of different things. We can see those LiDAR shadows. Over Little Rock, Arkansas, there's clouds occurring, and so we can't see the boundary layer there, so we don't even try. And then the black line is the boundary layer depth, and you can see that it's finding that maximum in the attenuated backscatter signal. So it's finding, in this case, those were clouds. But even when there aren't clouds, we can still find a boundary layer because of aerosols. There's just more stuff below where the boundary layer is being retrieved. So then we can look at boundary layer sort of averaged over the globe. So these are aggregated into 1 1/4 degree grid boxes. I can't plot 3 billion laser shots and have you be able to see them. So we aggregate them onto the 1 1/4 degree grid spots. This is from when first light occurred in June of 2006 through December of 2011. And this is only looking at the early afternoon, so about 12 noon to 3 p.m. And remember, when you're looking at these, that there's no deep convective clouds. So there's a little bit of a bias there if there's a lot of rain or something going on, that those profiles are not included in here. Okay, so we can see several different features jump out at you. One, you can see land versus ocean. There's a lot of heterogeneity, and the UVL depth is generally deeper over the land than it is over the water. You can also see summer versus winter. If you just look at the United States, you've got a shallower boundary layer there than you do you have a shallower boundary layer during winter than you do during the summer. You also see a lower boundary layer depth over equatorial upwelling. So where you have that cold water, you have a very stable surface, and so the boundary layer depth isn't getting very high. We also see stratocumulus cloud decks off the west coast of continents. You can see sort of that cloud top. And you can see the northern hemisphere storm tracks. And so what the storm tracks are is that you've got cold continental air going out over the warm ocean, and that warm ocean produces an instability, and so you get a deeper boundary layer. So you're getting that higher boundary layer in the winter rather than during the summer off North America and off of Asia.
I'm kind of surprised to see, like, I've been in Siberia, and it's in January, and it's a pretty cold place for boundary layer to be like 1,500 meters or something.
Yes, so some of the problems with this algorithm, I mean, it's great that it gives global coverage, but it's not as great at getting the shallow boundary layers, because you've got that minimum of 250. And so some of the biases actually come from getting aerosols that are being infected at higher heights, because it's not going to be able to detect that really shallow boundary layer close, over things like Siberia.
So it mostly works for kind of convective boundary layers, no?
Yes. It works where the aerosols and the clouds are about the same height as the temperature inversion. Is where it works best. I could have just focused on, sort of lower latitudes, but I wanted to be able to see the whole globe. You've got the data, should at least look at it. Okay, so this is the seasonal PBL depth change. So this map using June, July, August minus December, January, February. So the warm colors are when June, July, August, boreal summer is deeper, and the blue colors are when DJF is deeper. And we can see several different features jump out from here. The largest changes are occurring over the subtropical deserts. There's a big change between summertime PBL depth and wintertime PBL depth. And this is occurring both in the northern and southern hemisphere. If you see, oops, I will get this just before I finish my talk. You can see in the deserts in Africa, you actually have a pretty strong signal where in the austral summer, the PBL depth is deeper. So this is Africa, Middle East, Asia, Australia. The smallest changes are occurring over the water and the tropics. That's where you have the small seasonal cycle, which is expected. And we see the opposite signal over land and water. So, over North America, in the summertime, you have a deeper boundary layer. And then in the wintertime, you have that deep boundary layer from the northern hemisphere storm tracks coming off of, cold air going off over the Gulf Stream. The exception to this is over Antarctic ice. So in the austral winter, you have a lot of sea ice cover that's producing a very cold, stable surface. And so your boundary layer isn't getting as deep as it does in the northern hemisphere storm tracks. So we can sort of average this and look at sort of hemisphere averages. So we've got northern hemisphere, tropics, and southern hemisphere. Northern hemisphere is 23 degrees north and above. Southern hemisphere is 23 degrees south and south of that. And the tropics are in between. And you can see that you have that opposite seasonal cycle between the oceans and the lands in the two hemispheres. Over the land, the boundary layer depth is deepest over summer. Over oceans, it's deepest over the winter. Exception to this is in the tropics, where you actually have double maxima, and those are during the transition seasons. Because I've got the tropics going all the way out to 23 degrees, and so you're getting a little bit of seasonal influence at those higher latitudes. The largest seasonal cycle is over northern hemisphere land, because you have the least influence from the oceans to sort of moderate things, and the smallest seasonal cycle is over tropical water. So we can look at standard deviation or standard error of the mean, and this is sort of a measure of uncertainty. So this is the standard deviation divided by the number of observations. So it's sort of telling you, how many times are you observing it and how variable is it. So it doesn't take into account biases. So it's not going to take into account the fact that shallow boundary layers are hard to retrieve with this satellite. Which, when you're considering you're at 705 kilometers and you're trying to measure something at 1 kilometer, that's not too surprising. And it doesn't take into account that we're not seeing those cumulonimbus highly convective regions. So our highest uncertainty is over the tropics and the polar winter. Winter poles, and that's because of polar night. You're not going to be able to measure a daytime boundary depth if there's no sun. So that's polar night, and then deep convective clouds in the tropics along the ITCZ. We're not getting a lot of measurements. So the ITCZ follows the uncertainty follows the ITCZ and the rainy seasons. And with the lowest uncertainty is over water, and there's just a very low standard deviation. So retrieval rate, how out of those, millions and billions of observations, how many of those are we actually able to determine a boundary layer depth? So this is the number of found boundary layer depths divided by the total number of satellite profiles. So this does not include things like the Lidar not functioning. So if they have to turn the Lidar off because of solar flare, I'm not counting that against the retrieval. We find the highest retrieval is over subsidence regions. So when you have overlying subsidence, you're inhibiting that deep convection to form those deep clouds. So you're getting a pretty high retrieval right there of about 80% or higher. These are places like the subtropical deserts, stratocumulus regions, places where you think of deserts. There's a lower rate in convective regions, so where you have optically thick clouds, you can't see through those, and so you're not going to be able to retrieve a boundary layer depth there. So this is places like the ITCZ. Along the storm tracks, you're going to get reduced coverage. During the monsoon over India, during the Amazon rainy season. But the global mean retrieval rate is about 45%. So if you take that 45% and you multiply it by the 850,000 daytime profiles you're getting, you're going to get about 380,000 PBL depth measurements every day, which is an astounding amount of data that you can still get. So how does the Calypso boundary layer depth compare to other estimates? So first I compared it to aircraft. So this is determining boundary layer depth from aircraft as they're taking off and landing. They have instruments on them that they can measure temperature and humidity. So what I did was I looked at takeoffs and landings that occurred within 100 kilometers of a Calypso overpass and within half an hour of that overpass. So if you look at those, you get 165 different airports that have a takeoff and landing. Unfortunately, most locations had fewer than 20 co-locations, so this is a bit of a limited comparison. They're concentrated in the United States and Europe, and there are no aircraft over the southern hemisphere, but we can still draw some conclusions. So most Calypso boundary layer depths are within about 25% of the aircraft, and almost all of them are actually within that 40% that the radiosondes are able to detect of a spatial average. Over the southwestern United States, there's a lot of heterogeneous terrain, and the aircraft are giving a deeper boundary layer depth than the Calypso satellite is. And so we're not entirely sure if that's because of the large spatial difference between them and the heterogeneous terrain, or if that's something that's going on with the Calypso retrieval. Also, over high latitudes, the Calypso is detecting a deeper boundary layer depth than the aircraft are, and that's because of the biases within the Calypso satellite. That's because we can't estimate the very shallow PBLs because of surface noise. So we can also compare Calypso satellite to GEOS-5. So on the left is Calypso, on the right is GEOS-5. GEOS-5 is a model. And they're both looking at June, July, August, and the PBL depths are relatively qualitatively similar, but there's a lot of differences. And this could be due to a lot of different things. First of all, Calypso is measuring at point measurements. Satellite track as it's going along, it's measuring different profiles. Whereas GEOS-5 is looking at grid cells. This is a half degree, so you're looking at half degree versus a point measurement. Calypso is looking at 5.5 years, whereas GEOS-5 is only looking at about 20 years. Calypso measures once every 16 days, so about once every 2 weeks, whereas GEOS-5 is able to determine boundary layer depth every 3 hours. And Calypso is looking at roughly clear sky. It doesn't have those deep convection. It allows boundary layer clouds, but none of the deep cumulonimbus, whereas GEOS-5 is looking at all sky. But there's also looking at different methods. Calypso is looking at how high are aerosols being lofted, where are the boundary layer clouds, whereas GEOS-5 is looking at the eddy diffusivity. It's looking at the amount of diffusion, how high is the model say that things should be getting. And so this motivated a study of the different definitions of boundary layer depth. So studies find that boundary layer depth is important. Different definitions can produce PBL depths that differ by 10 to 100%, hundreds of meters. And that can have a big impact if you're trying to measure tracer transport. Some definitions are applicable to some measurements, but not to others. So for instance, in the model, we look at diffusion, but you can't look at that with the radiuson. With the radiuson, you have to look at something with temperature. So they're not always applicable to one another. So it's best to be able to make comparisons using the same definition, if you can do that. So this motivated us to study the definition of PBL depth in GEOS-5 and just to isolate that impact. Okay, so we looked at 7 different methods. The first 3 depend on the eddy diffusivity, which I have an example of what that is. It just relates the turbulent flux to the gradient of the mean variable. So the flux equals the eddy diffusivity times the vertical gradient. So it's basically just measuring how high are things being measured or being vectored. So the first uses the eddy diffusivity and a threshold of 2. And this is the default in GEOS-5. That's what's being used in MERA if you ever use that reanalysis. And that value of 2 is used everywhere. So it's being used over Siberia, it's being used over the Amazon rainforest, it's being used over water. It doesn't change. So there's not a lot of flexibility in adapting to different locations. The next 2 depend on 10% of the column maximum. So you have a profile, and you look at what's the maximum of that profile, and we make that threshold 10%. So the eddy diffusivity has sort of a maximum within the boundary layer, and then it decays off. So where does that decay? And that's going to depend on the 10% of that column maximum. And we looked at it in 2 different ways. The first way includes a radiative plume. It includes the impact of radiative cooling at cloud top. And the second one is neglecting that radiative cooling. And the idea behind that is that then we can evaluate the impact of clouds. How much are clouds impacting our definition of boundary layer depth? The next 4 methods are more meteorologically based, more of what you would look at with, for instance, radiusons, more of a traditional definition. The first is using a bulk Richardson number between the surface and progressively higher heights. The next 2 are looking at a local gradient Richardson number just between 2 different model levels, going progressively higher in the atmosphere, and looking at 2 different critical values to sort of look at the impact of changing that critical value. And the last method is looking at horizontal TKE, so just diagnosing turbulent kinetic energy to try and look at what is the impact of doing that, and that's sensitive to things like wind shear. So what is wind doing to the boundary layer depth? And just as a reminder, the Richardson number is equal to the production by buoyancy or consumption of turbulent kinetic energy divided by the shear production. The reason we're looking at the bulk Richardson number method is that it's currently being used in a large intercomparison project. They've done a lot of studies with radiosondes using this definition, and now they're starting to look at models and what does the bulk Richardson number do to boundary layer depth in models. So model setup, we use the GEOS-5 model, which is the Goddard Earth Observing System model, version 5. We used a free-running atmospheric model from January of 1990 through May of 2013. We initialized it using MERA, which is that reanalysis. It's taking the underlying model and assimilating observations. We looked at C180 is the horizontal grid resolution, which translated basically means about half degree, but it's on a cube sphere, which is sort of a different kind of grid. It's not the standard lat long that you think of. And GEOS-5 has 2 different turbulent parameterizations that work together. And this is sort of how we're measuring boundary layer depth, is within these parameterizations. The first one is Louis. And for Louis, the eddy diffusivity, that, translating the flux into the mean gradients, and vice versa, is computed as a function of the Richardson number. So it's a little bit more sensitive to the meteorology and sort of traditional definitions. And that one is actually dependent upon the boundary layer depth, so there's a feedback for those. And with LOC is the second scheme, and for that one, it's computed based on a surface plume, so warm air rising through the boundary layer depth, and also on a radiative plume, so cool air from cloud top, radiative cooling and sinking. And so that's actually where we're getting our impact from clouds. So we wanted to be able to make broad generalizations. You know, every different grid cell is going to have a different boundary layer depth. And that's partly because it's sensitive to local conditions. It's sensitive to the terrain. It's sensitive to local heating. It's sensitive to mesoscale circulations, land sea breezes, mountain valley breezes. It's sensitive to roughness. And so we wanted to be able to make broad generalizations and draw conclusions globally. So what we did was we actually aggregated our results onto the Koppen-Geiger climate classes. So these are for land only. So this is what they look like. So this is an updated Koppen-Geiger classification system. The paper came out in 2007, but this is a pretty old idea of these classification types. There's 5 basic classification types. They are tropics, arid, temperate, cold, and polar. And there's sort of a way of making similarities and making comparisons between spatially different regions but have similar precipitation and temperature characteristics. Okay, so even within these climate classifications, even though they have similar temperature and precipitation cycles, there are different behaviors that exist. Proximity and climate type are not enough to diagnose the boundary layer depth response to something like sensible heat flux. And so these aggregated results are going to show general behavior, and they're not going to be similar to any specific location or time. So some examples of these regimes. So this is the hot, arid desert climate class. So this is places like the Sahara, the Australian desert, the Chihuahuan desert in Mexico. We've got sensible heat flux along the x-axis and boundary layer depth along the y-axis, and this is just a scatter diagram. And the Australian desert is highlighted in color according to evaporative fraction. And if you're not familiar with evaporative fraction, it's related to Bowen ratio, but it's the latent energy divided by the sensible heat plus latent heat of the latent energy. And this is actually useful over the deserts because over the deserts, the Bowen ratio is divided by latent energy, and it can become unbounded. So this is a sort of a better way of looking at the deserts according to some people. And we see 2 different regimes. We see a low evaporative fraction regime where the boundary layer depth is a little bit higher, and there's a lot more variability, or a lot less variability, with boundary layer depth with sensible heat flux. And we have a high evaporative fraction regime. So that's slightly lower sensible heat flux, but a higher evaporative fraction, and you're getting higher boundary layer depths. We can also look at the boundary layer depth over the Sahara, and we see that there's a lot of spatial heterogeneity there as well. This is June, July, August boundary layer depth using the default that threshold of 2 definition. And we see that we're getting deeper boundary layer depth over the western part of the Sahara and the Arabian Peninsula, but we're getting lower boundary layer depths along the coast. So there's still a lot of spatial heterogeneity that these general climate classes are not taking into account. A third example is over the tropical rainforest. We've got 10-meter temperature along the x-axis and boundary layer depth along the y-axis. Again, this is a scatter plot, and the colors are associated with 10-meter relative humidity. And we see sort of 2 regimes that are separated by the optimal temperature. And in models, the optimal temperature above that, evapotranspiration is limited, so you're getting less latent heat flux. And with this lower humidity, the boundary layer depth is actually increasing with temperature, whereas at lower temperatures, the boundary layer depth is decreasing with temperature. And it's because of just so much latent energy, and all that solar radiation is going into evaporation. So then we can look at diurnal cycles. What does the boundary layer depth look on a diurnal cycle? So this is the cold climate class. We can see that the local Richardson number, which is the orange and purple lines, are much shallower than the other definitions. And there's little sensitivity to the critical Richardson number. Those 2 lines are pretty similar. The other methods give similar midday results. During the summer, they're about 1,600 meters. And there's a negligible impact of the radiative plume. That's the red versus the red dashed line. However, during winter, that horizontal TKE method, the blue line, is a little bit deeper than the other methods, and that's because it's sensitive to those storms, it's sensitive to that shear, and that's producing a deeper boundary layer. The black dots represent mean boundary layer depth estimates from radiosondes. And so we expect these to be pretty different because these are just point measurements in a couple of locations. So they have a couple of different locations that are measuring boundary layer depth, not the full region. And they were defined using the bulk Richardson number, which is the green line. And during summer methods, they show that relative to the radiosondes, all of the methods are actually overestimating that nocturnal boundary layer, which is really important again for that tracer transport. However, midday boundary layer depths, when you sort of squint your eyes and remember that these are just point measurements in comparison to a much larger region, they're fairly similar. So we can look at the hot arid desert. And what we see is that the boundary layer depths that are dependent upon Richardson numbers, so that orange, purple, and green line, they're getting a much shallower nocturnal boundary layer. Their boundary layers are about 290 meters for the bulk Richardson number method, whereas the eddy diffusivity methods, the definitions that are currently being used in GEOS5 in MERA are closer to 800 meters. And so there's about a 500-meter difference between the nocturnal boundary layer in one method versus another. And the radiosondes are estimating an even shallower boundary layer. So there's definitely some improvement that can be made. We can look at the tropical rainforest, and you can see that there's a much stronger impact of the radiative plume. Clouds are much more important in the tropics for determining boundary layer depth. They're specifically important during the nocturnal boundary layer and evening transition. And the bulk Richardson number method produces a PBL that is quite a bit shallower in these warm, moist conditions. In this case, about 400 meters shallower. So we can look at this a little bit more closely. So these are different profiles. On the left is Richardson number is the eddy diffusivity. And remember, so the blue line is the Louis eddy diffusivity, and it depends on the Richardson number. So it's a little bit more meteorologically based. The black line is the total eddy diffusivity. That's the one that's being used in the default threshold of 2 method. The middle panel is the bulk Richardson number in green and the virtual potential temperature in black. And on the right is just a zoomed in image of the virtual temperature. And these are taken from a location in the Amazon rainforest. The horizontal lines indicate the boundary layer depth estimated by the different methods. So on the far left, it's using that default, that 2 threshold boundary layer depth. That's how high it's picking that boundary layer depth out. And in the other 2 plots, the middle and the far right, are using the bulk Richardson number method. So what we're seeing is that the bulk Richardson number is becoming stable at a much lower height than the eddy diffusivity is falling back to its threshold. And the Louis eddy diffusivity is actually falling back, more similar to the bulk Richardson number. And again, that's because they're so more related. And these are due to a small inversion in the virtual potential temperature. So there's some sort of disconnect between what the turbulence is doing and what the meteorology is doing in the model. So we can look at the radiative plume impact. So this is the eddy diffusivity method using that 10% column maximum threshold with the radiative plume minus the same thing but without the radiative plume. So this is sort of isolating the impact of clouds. And we can see that there's a diurnal impact of the radiative plume. The largest impact is over land during the evening transition. So this is because the clouds don't dissipate. Just because the sun goes down, the clouds stay put. And so that's sort of influencing and keeping that boundary layer depth a little bit deeper than when you neglect the radiative plume. And there's also sort of a stripe along the southern hemisphere about 30 degrees south. And this is because in the model, there's a small prescribed cloud radius there, and there's also the boundary layer clouds are present. And so these small cloud droplets are leading to an increased long wave radiation flux. So you're getting more of that cloud top cooling there. So conclusions, you guys made it to the end. Boundary layer depth definition matters, and you need to be able to isolate its impact. We looked at 7 different PBL methods and compared them using a single atmosphere. And what we found is that you can have a boundary layer depth that can differ by 400 meters or by hundreds of meters. The Richardson number based methods collapse better for the nocturnal boundary layer, or collapse lower. The bulk Richardson number method, the one that's being used in the large intercomparison project, that one is producing boundary layer depths in the tropics that are shallower during midday than the default GEOS 5. So there's some sort of difference between what the meteorology is saying and what the turbulence is doing. And the clouds matter most during the evening transition and at night. If you look at the Calypso conclusions, deeper boundary layer over land than over water, which is something we would expect. The PBL depth varies with solar insolation, so it's deeper during summer than during winter over land, and the opposite over the ocean. The seasonal cycle is opposite between the land and ocean. The largest seasonal cycle is over the subtropical deserts. The Calypso retrieval percentage is greatest over the subtropical oceans, where you have overlying subsidence that's preventing the deep optically thick clouds from forming. Uncertainty is greatest over the tropics, the winter poles, and the convective regions. And this data set allows a global study of boundary layer depth, something that's not able to be done from the surface. And with you're getting over 100 million retrievals every year. If you multiply out that 380,000 boundary layer depth measurements every day times 365 days, you're getting quite a bit of data. So that's something that just certainly should be considered, I think. And with that, I'll ask if there are any questions.
Questions? Yes, Bob.
Could you just remind us of the definition of the bulk Richardson numbers? It's all
Okay, so the bulk Richardson number was used in the Seidel et al. 2012 paper, and what they're doing is they're assuming negligible surface winds. So forget that, and looking at the difference between so it starts at the surface and going progressively up higher, and what is what's the potential temperature, the virtual potential temperature gradient between successively higher heights and the surface divided by the wind speeds. It's like G over theta V times delta theta V divided by delta wind speed.
There's McGrath.
Yeah, two questions. One is, say, cosmic, the satellite cosmic, I don't know whether you know.
The satellite.
Cosmic.
Cosmic.
Oh, cosmic satellite.
Yeah,
Yes, with the GPS.
That's right. That has lots of profile data, and some people are using that to do boundary layer.
Yes, they've actually made a lot of progress. At AGU last year, I saw some of the people with the GPS RO team. There are a lot of great advantages to that data. It doesn't, it's not impacted by those thick overlying clouds. But they do have a larger swath, but thanks to they do the occultation measurements, and so they have much an average over a much greater area, whereas Calypso is much more of a point measurement. So yeah, that's definitely. I've talked to them, and I've sort of just looked at their papers and sort of compared, and we're getting qualitatively similar results. So that seems promising.
And then regarding the definition, so that is important only if you need to do comparison with, say, another data set. Is that right?
I mean, it's important if you want to do comparisons. It's also important. So in GEOS 5, the boundary layer depth actually feeds back into the model and determines the amount of diffusion that's occurring. And so if you're having too much diffusion at night because our boundary layer depth is too deep, our boundary layer is too deep, that's going to impact our diffusion.
But then there isn't a comparable measurements to compare with. Is that right? Because the definition from the satellite is different from what's defined.
Yes, exactly. And so that's why it's sort of best if you can to try and compare, apples to apples, compare similar definitions and similar sorts of data sets.
Yeah, Margaret.
There are some new methodologies that have been used for high vertical resolution radiosondes that can actually get estimates of vertical diffusion. Now, of course, you're still stuck with the 00Z, 12Z problem, but I don't know if you you know about these or if that might be useful.
I didn't know about them using that to determine diffusivity. I do know that they do have some high resolution radiosondes.
I could show you some results later.
Okay, yeah. Last I heard they were more concentrated in the US. Is that
Well, they're the
is my
only
memory
ones.
serving?
They're the only ones who are making. Well, they're the only high resolution radiosonde data which have been made publicly available.
Okay.
They're the easiest to obtain
Okay.
from here.
Okay.
That's Hilary.
So then,
Yes,
one
I don't
more
mind.
question.
Yeah, so I have another comment. Several modeling centers have implemented the Calypso simulator into the model.
Yes.
Then you have an apple-to-apple comparison with your analysis.
Yes. I actually that was another thing I actually saw at AGU last year, and I'm hoping to see again this year. It looks really interesting, and the way they're doing it is they're doing it sort of after the fact. They're running the model and then computing the backscatter sort of after the model's been running. And for us, we're trying to look at it sort of live and actively running, because the sort of the motivation for looking at these different definitions is we want to be able to change the boundary layer depth that is actually being used by the model to determine the diffusion. So we're actually going to be impacting the tracer transport by changing that boundary layer depth. And that's hard to do if you're not determining the boundary layer depth until after your simulation is over. But yeah, no, I've seen those results and they're pretty cool.
There's one more from anyone.
I'm motivated by that question. Has there been a methodical comparison of PBLs in the various climate models?
That's actually one of the things they're doing with the big, large intercomparison project. I don't know if you know Andy Jacobson at NOAA.
Yeah.
He's sort of spearheading that effort, and I believe he has a talk this year at AGU. I don't know if anybody's going. But yeah, no, that's definitely, they're all using the bulk Richardson number method in all the different models, and I believe they're looking at more like reanalyses as opposed to straight up free running model. But I think it's going to have some pretty cool results.
Yeah.
Anybody else?
So no more questions, so let us thank Erica for such a wonderful session.